Okay, should be working now. So, like I said, on Wednesday, there is from 11 to 1 p.m. a study session with me and everyone. Y'all can just also come in and work problems and break out into groups. And if I'm helping someone else, y'all can work together, all of that stuff. I think it'll be good. And then otherwise, do we have any questions before we get into the actual final exam topics? Okay. I have space up here. Okay. Then I'm going to, can you do me a favor and close the door, crack it? So I know y'all said he hasn't gone over what's going to be on the exam, right? Okay. So I've seen it. There's not gonna be a part A, correct?
What does that mean? Like a party?
Like a multiple choice section. Yeah. Yeah.
That'd be crazy, by the way.
So there is all in every year I've ever seen, there's always a part A, but he's not doing that this semester. So it is just gonna be the problem solving portion. Um, good and bad, right? But that's it. So we got, it's gonna be 4 questions, and I do always say now, there is a chance that the night before the exam, he changes his mind and puts a different problem on there. That happened once. Everyone got really mad at me because that's not what I told them to study. So don't sue me. But these are, as of right now, these are the topics that are going to be on the exam, Just have to give that little disclaimer, but I know for sure op amps aren't going to be on there. So I know that that's going to be a question. So topics are another complex admittance, a switch, first order, there's going to be critically damped second order, and I'm just going to say Thevenins/Nortons. So that's what's going to be on there. There is, and I have to be at least kind of vague because I can't tell you exactly what the problems are going to be, right? Um, there is a decent chance that there's a question similar to the Thevenins or Nortons or whichever one it was that was on your midterm 2, right? I think that threw everyone for a loop a little bit. We're going to work it out today. So I'm going to work it out for y'all today. And then I have questions for all of the other ones that we're going to go through. I'm going to start with the one from your midterm since you've seen it before. Before I go to that, do you have any questions though? Saw the previous video. Uh, I don't think that's going to happen. Um, I kind of spearheaded that and did all of the math for it and gave him the Excel sheet. I don't think that he is going to be able to do that this semester. So I would not count on that.
For
Unfortunately.
the critically adapted. No, but, right out second order equation.
No, so you're gonna have to like find the P. It'll look very similar to this. Can you read that? Yeah. So calculate for critically damped, calculate the value of the variable, and then calculate the exponent P. Past the exponent P, don't need to worry. Second order is rough and I always forget. I had to look over it again today. But yeah, anything else? Coolsy. Sounds good. So y'all good with doing this guy first?
Yeah.
Cool. So the scaled resistive network, I'm going to read the question, is driven by an independent current source, JG. Calculate the values for the source, JG, and the transconductance, GM, that will produce the Thevenin's equivalent of this. So where did everyone get lost? If you did it great and this didn't trip you up, that's amazing. But
Well, I just thought, we needed it because we're gonna solve for nodes, I thought, but I just chose a node above G1, a node above GMV, whatever, then a node above, G3. And then I tried to solve it normally as much as I can that way. I didn't know what to do. I didn't finish. This is the last question I did. I didn't get the part where I put the end part.
Okay.
Right, whatever.
How would
okay.
we know how many nodes to try to calculate?
So that is a good question. And so we know, and this is, I think most of y'all were there. If you didn't come to my last review, I really recommend watching it because a lot of this stuff was on there. So same with when you come in the study session, if you come ask me how to do MAME and you haven't watched the review videos, that's not the best. I would appreciate if you watched them before you come ask me that type of question, and I hope that's fair. But yeah, when we do Thevenin's, we draw this here, right? Just simple. We're gonna draw that. And so from here, after we draw that specifically, we're gonna count the number of nodes. If there is just a wire connecting 2 points, that is the same node. If there is not an element between 2 points, it's the same node. And that you kind of think about more with ground and you see it more. Like this, it says ground is right here, but how far over does ground extend? It is the whole thing is ground, right? So that is node number. Technically, it's node number 0. It's not node 1, but I'm just going to call it node 0. And then we see up here, right? This is where stuff connects. How many nodes are going to be there? It's just one node here. So this is all wire. So that is node number 1. And then over here, same thing. That is going to be node number 2. So this is just a 2x2 matrix.
That's why there's so many zeros in mine.
Yeah.
Mine had a million zeros.
Yeah. What were you gonna say?
Could you explain how those count?
So, oh, yeah, sorry, meant to say that. You know how in meshes, and it makes more sense, your matrix is how many, it's n by n of how many meshes. Name is the number of nodes minus one.
So it's because the, what you call this, current source and resistor is are they not parallel with the GM meter? There's that,
Right.
like the JG and the
Mhm.
G1 is also, they're all in parallel with each other, right? So they're
Yeah.
all kind of connected to. the
Yes,
same node.
exactly. Yes, 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 yes. These are all in parallel. They are both connected to ground and node one. Um, so yeah, they're pretty much like in a MAME, they're all in the same branch. They're all connected to the same nodes. Um, so does that make sense of n is equal to the number of nodes minus one, where meshes, I don't know if that makes sense, but that's how big your matrix is going to be. And that's why I wrote 0, because your ground is never one of your nodes. That is what the -1 is your ground. Does anybody want me to re-explain that, or y'all tracking?
Keep it ground again, keep it ground.
So we say it's the number of nodes minus 1. We say -1 because we don't count ground as one of the nodes for name. Ground is a node, but we do not count it we don't want to solve in name like what's connected to both one and ground. We don't want to use that for our calculations.
There's just like zeros everywhere, but
Kind of, yeah. And man, I don't know if I have a really solid definition of why we don't use ground, other than we don't use ground for nodal analysis.
yeah, just because.
Yeah, that is,
It's like a really good reason.
I'm sure there is, but I'm blanking on it. And that is just kind of one of the ones where you remember that. And now I'm gonna have to think about it. So, but yeah. Does that generally make sense? Okay, cool. Also, if you want to take a picture of this really quick. Okay, cool.
So in order to do the main, would there
Yes.
be 4 meshes in there, or would you just do
So yes, there would be 4 meshes. But you couldn't do MAME here because remember, everything has to be voltage sources. So you would have to condense all of this down to a voltage source, which then would make less than 4. Because that would all condense down.
I thought it would just be the G1 and J2 that condenses.
You can condense that too. It just would make another dependent source. Yeah. But anyway, this is kind of the starting step. And I didn't mention that I'm going to redraw this. This is going to be E not. Man, I just finished saying I switch over.
would it not be J naught?
Yep. I just finished talking about how it would need to be current sources, and I wrote a voltage source. So yeah, that should be J naught. And yeah. Starting off good. So now that we have this, what is the next step? We're just going to start writing the resistive matrix. So we're going to do this, make that a little small. What's going to be in the first one? And then what? -1, then what? -1, 5. Made that, I don't know why I made that so small. And that's going to be BN1, BN2. This is
3+1 and then -1 for the shift.
yes, yes.
Yeah, 4+1.
Yeah. So this, the only thing that's actually shared in this one between 1 and 2 is this right here. Because remember, we're not counting ground. We're not counting what's connected over ground. So we look here, the only thing that's connected is this 1 Siemens. And that's why it's 2 -1s there. That's, I wrote that down. No, so whenever we do name, we always have everything in, we have everything in conductances and current sources. And I go into Thevenin's and Norton's super in detail on my last review. I'll go over it again today, but definitely go back and watch that one. But now you can actually see it. So what's this going to be equal to? G plus GM V3. Perfect. And then what about the other one? Just J naught. That's all that's going into VN2. So this is the easy part, right? This is, you don't have to start solving backwards. We're just going to put that there. So next, what we're going to do though, is we're going to separate it out. Even though we don't have numbers yet, we still know it tells us that JG is independent, right? So we know that that is going to be down here, the independent matrix. And then obviously GMV3 is dependent because it depends on V3. And then our J naught is always by itself. And we put J naught over here. Do we all agree with what I went ahead and did here? Because we're just separating this out. It's not added here. This turns into these 3 matrices added together. So now, like I said, what's the independent sources here? So is J0 independent? Sort of. It is independent, but because we turn it off and then turn it on, it's easier to separate it out into 2 matrices. You can keep it in the same matrix and then just remember to turn off only J naught and then turn off all of the other independent sources. But I think it's easier to just go ahead and separate them out. So you can literally just say that matrix goes to 0, matrix goes to 0. Exactly. And so because of that, we're gonna do just here. If you don't want to do it that way, that's fine, but visually it's a little easier, I think. So we're gonna do that today. And then over here, GM V3, and then nothing there. So not too bad. So the only thing now is what do we do here now? Yep. So let's see, where is V3? V3 is right here. So our variable here right now is voltage, right? We're looking for a voltage. So do we need to do any equation, or is it just going to be our node voltage? Node voltage. Sweet. So up here, well, actually, let's start from the plus. What's the voltage right there? So V3 is equal to 0, and then what's down here? So it's going to be 0 minus Vn2. How do y'all feel about that?
Other resistant in series above it between V2 and the V3, would that be different too? That we have to account for that.
We wouldn't give you that name.
Because there's no, we're not counting ground node, so it's just 0.
So ground is inherently 0. The voltage at ground is 0.
What? The other way around? Go from the down side.
So that's because of this plus and minus. Can y'all see that? So the highest is always at the plus because it goes from high to low. So the highest voltage here is at this node. And so that's why we start with 0. And then it goes down, and so we subtract the lower one. If it were plus minus, then it would be the other way.
If it was- Oh, it's 0, right?
Yeah. Yeah, if it was plus minus, it would be Vn2 minus 0, which just equals Vn2.
Right.
But instead, we're just going to have V3 is equal to negative Vn2, which is pretty easy because let's do our
And will we give them a GM equals,
no, we have to find that.
What is GM?
It's
That's right, I mixed up. I thought it was supposed to be given every question.
no, so it says up here, right? It says calculate the values for source JG and transconductance GM. So it's telling you that you need to find what it is. It's essentially just X. In electronics, a lot of times they separate out transistors and op amps into dependent current sources, which you'll probably see more next semester. And conductances are everywhere in analog devices, and there's a million different subscripts for them. And I always got them mixed up. Electronics was not my favorite. I was a circuits person, obviously, but you'll see a lot of GMs and Bs and Ds and all of that. So it's one of those. It's my really long-winded answer for that. But you can just treat it as an X. Does that make sense?
Yeah.
Okay, cool. So coming back down here, we see V3. We need to separate it out into a 2x2 matrix times our Vn1, Vn2. Do we remember why? Does everybody remember why? Exactly. We want to be able to subtract this to the other side. And for you to subtract matrices, they have to be the exact same in format. So to subtract something from a 2x2 times a 2x1, you need to make it into a 2x2 times a 2 by 1. All we do here is find the coefficients for all of this. How many VN1s are in the first? 0. What about here? GM. There are GM many VN2s. Then bottom, 0, 0. So that's all. Now what we're going to do is we're going to subtract over here. Subtract. This gives us a very easy subtraction of 4, -1 minus GM, -1, 5. Times VN1, VN2. We all good with that? Sweet. Here's the fun part.
Negative GM, or it's a negative V3.
Ooh, oh, you're so right. You're so right. You are so right. Good catch. That's what happens if you try to do it in your head. This is what happens.
Always gonna be two.
It's supposed to be negative VN2. So
How come, wait, oh,
So we plug in V3 this is equal to negative GM VN2. So now we have negative GM, we subtract negative GM, and it becomes -1 plus GM. Apologies for that. So now we have one matrix with JG and 0. Dang it. 0, J naught. Yeah. So we have an issue now. We have 2 unknowns. However, how many equations do we have? So whenever we solve for 2 things, right? We solve it 2 different ways. Which means we kind of have 2 equations. So if we remember to solve for Thevenin's or Norton's, but I'll do Thevenin's, obviously. To find E Thevenin's, turn off, set J naught equal to 0, and find solve with independent sources. And then to find R Thevenin's, set J independent equal to 0, and set J naught equal to 1. Do we kind of remember this from? So this is where we get, there's 2 equations. One of our unknowns is JG, right? So do we have one of these equations where we just kind of get rid of that? Sorry, it's J independent. So if we're solving for R Thevenin's, we set JG, set that equal to 0. And now we magically only have 1 variable because we set that equal to 1. So to find, just write this down. J independent equal to 0 and J not equal to 1. quickly write this again for -1. Oh, jeez. -1 plus GM, and I cannot do this in my head. So does anyone want to get out their calculator? Oh, and then, so I guess we need to go over how you solve in your calculator. So I've gone over this before, but I will go over it again. Let's see, is it gonna like me? No, of course it's not. So no, we're using the RTH equation to find GM. Because normally we're solving for this. But right, sorry. Backtrack. What I said is true, but we aren't going to find GM yet. What we're going to do here is we are going to solve for VN1 and VN2 in terms of GM.
So for something X.
Yes. So both of our answers here are going to have GM in them. And then what we're going to do is we're going to plug in, am I doing that the right way? How'd you do that? So let's, yeah. I'm blanking. Let's just see what happens. Let's do that. Let's see what happens if we just try to put a variable in there. Hmm? What is it? That's not that ugly. Let's do RREF. GM, 0, -1. Can y'all see that?
Is that when we do inverse of the part of our matrix, which 0, 1? Doesn't, yes, we do.
Yes.
So when you put in GM, it'll not have one variable. Like it won't be like G with a separate variable and M with a separate variable.
Correct.
Oh, it won't be that?
No.
What is it? What's it 1 minus 0, 1?
So it can be plus GM.
Or I think it's 1 minus.
Because I put it in wrong.
Already in the middle.
Yeah, so I did REF. So I did the row reduced echelon form. Okay. No, sorry. That was not at you. Oh my gosh. That was at the screen not focusing.
No, I get it.
So they're the exact same. So doing this and doing times the inverse, and I'll do it real quick. Yeah. It's I always say it's less buttons. And so yes.
but they,
I think that you have to redo it. I don't,
even if oh, I know that, so once you create it, whatever, you want to add it actually. I don't know how to do that.
yeah, I don't know. Yeah, so you see that they are. Hmm. I'm blanking. How to do that. I just totally forgot. What do y'all think?
That's the way we reach,
Mhm.
maybe we say GM equals something, and then we just plug it back in the something else.
Isn't there a solve?
Yeah. It's it's
I don't know, like GM is like some variable, but if we just replace it with stuff we know, then we can put that back in
mhm.
somehow with something.
I think this is an option that maybe like software GM, with G for this. I never got to work though.
Two by two, inverse.
No, I think
No, I think it's two for one, two for one, it's like V and one and V.
Y'all, I'm dumb.
You missed something.
How much you got those far back there to go?
No. Like this is still correct, but we kind of forgot. We were given the answer. Okay. So we're trying to find, do we use the E Thevenin's or the R Thevenin's equation for this? We found R Thevenin's. So which of these two did we just solve for? Which of these would be R Thevenin's? And the reason is VN2 is where A to B is. And so we're trying to find A to B. So we're using the second one for all of them. So we just got this equation of 4 over GM plus 19. We know that 4 over GM plus 19 has to equal 20. Now we solve for GM. I just was forgetting the easy part. So
So we disregard the top one, the 1 by 2, because that one's a 0.
That was for node one.
Yeah.
mhm. So to find RTH.
Is it equal to 0?
Hmm?
You said 4 G plus 19 equal to 0? That's why, because that's why I put it 20. Yeah.
Mhm. Hello. And so now, when we do the solve, okay, kind of see that menu 3, 1, right? So, or just type solve. And then we can just do 20 is equal to 4 over, and you can either type GM or you can just do a random thing of X, comma, yeah. Yes.
Why do we use R covenant and not E covenant?
So the whole reason that we set it equal to 0, 1 was because we set J independent equal to 0 and J not equal to 1, right? That is the equation for R thevenins.
Oh,
And so this whole thing was, okay, we can find R thevenins here. And that is what this equals. That makes sense? Okay, cool.
so now I have geometry to find JG.
Exactly.
Alright.
So now we're going to do the exact same thing of turning J naught off and just using JG. And now, no, I think we still can't do the solve yet. We still just put it in as variables. We do the solve after. What'd you get?
20? Oh, hold on. I got 3796 over 20. For negative that.
Negative 8.
Do that in the decimal form.
Yeah.
Is it 20 or 200? Oh, it's 20. It's 20.
Oh, it's 20.
Not 200.
Alright, so I get 20. I get that answer, but for 200.
Then you got negative 18 something.
Yeah, it should be 20 plus 4 over x plus 19.
Oh, that's because I put 200 first. Yeah, no, I got that, yeah.
Okay, cool. So I'm just rewriting this. It's the exact same. You don't have to rewrite it. So let's just go ahead and plug that back in. And remember, we can just arrow up and hit enter. And we can't really see that. And now I can just come in, do 0, and I just do J. Yeah. And so now here we see that J is equal to GM plus 19. Right? But we know what GM is. Can you all see that?
Repeat what that step was for again.
Okay, so we, instead of finding R thevenins, we did E thevenins. So we did the process to find J not to 0. Solve norm. So this is just how you would normally solve name. And just we set J not equal to 0, and then we're just solving that, which is the process to find E thevenins.
What you're getting exactly.
Exactly. So what we do here, and we're doing the exact same thing. I just plugged it in with the variable J, and we get here J over GM plus 19. But we know that J over GM plus 19 is equal to 0.75. And so now, and there's probably a cleaner way to do this. And I
Very important. Negative 18.
exactly. Crap. I actually didn't do that. No, you're good. That's my bad. So,
That's your beginning.
Ah.
You're getting. I got one problem.
you got 25 and then 5.
Yeah.
So you got 25 times J and 5 times J.
Yeah.
So, but remember, we were solving for E Thevenins. So E Thevenins is going to be the bottom one. And so we're saying that E Thevenin is equal to 0.75. So 0.75 is equal to 5 times JG.
So, is ETH always, or is ETH always like bottom matrix, or is it just because of the circle?
So that's, remember, we're trying to find E Thevenins from A to B. J naught, or the second node, really. See how node 2 is the node from A to B? That's why we're using the second node. Yes. JG, what's JG equal to? 0.75 divided by 5. 0.15. Or I like 150 milliamps. And then now we plug in okay. And then what I would do, and I think there's different ways to find GM, because now that we know JG, the way that I would do it is come back to this and take out GM and do solve it again with our known JG now. But you could probably go different ways to solve it. But this is what I did. Because that's what we solved for JG, right? Y'all tracking?
Oh, I just solved for JG, and how is, it's like a different way to solve for it? GM, what was this for again? What was the matrix that was just?
Y'all, I'm tripping. Okay, we solved for both of them. I thought that there was another step. We're done.
Yeah.
That's why y'all were looking at me like I was crazy. So we're done. That's all you need. That's what it asks for. So a little tricky, but not awful, right? Do you think you could do it again if you were given a similar problem?
I guess the law would change when it's north, it's like north of the voltage sources, right?
Mhm.
And then I guess what would that version of O, instead of finding GM, you have to find something else.
So realistically, he could have said find anything in this matrix. GM just happened to be the multiplier of the dependent source. That's all GM is. And then JG is just the independent. So it would just be a independent voltage source. But he could have also asked if you wanted to find like G2, or he had another independent source. He could say that you had to find, this source. So like you had 2 batteries. You just say find the other battery. It's the exact same process, but because you turn one off and then you turn the other off, you should be able to cancel out one of the variables and solve for it. Have an equation where you only have one variable. So whichever it ends up being, actually not whichever. It'll always be start with this one. Right? Because you turn the independent source off, and that's going to be one of the things you're solving for. So
The one that likes to start like one of being one.
mhm. You'll start off.
The brain will, you can turn off, solve or whatever, and no variable from that.
Mhm.
Substitute the value for that small,
Exactly.
and then write down the box.
Mhm. And it all comes back to this. And then this is the one that you're going to end up starting with.
The units per GM.
Siemens. Conductance. And conductance is 1 over resistance.
Just real quick.
Yes.
You plug into the calculator and get those two fractions.
Mhm.
Mine says 5 times J on the end one. Is that the one we utilize? Looks like this. Is that correct, or did I do something wrong?
Oh, so you have to plug in the negative 18.8 for GM.
Oh, okay.
Okay, so let's go ahead and move on to the next one. We good? Okay, we're gonna jump to second order. Because that's the only thing that we haven't done yet. So the other two are realistically just reviews of the reviews. Second order is scary, but it's all okay. Have y'all looked at the chapter Z1? Read it. Chapter Z1, it's in your materials. It's in your materials posted, right? Okay, cool. It's probably the second best thing Russell has published in his materials. The other one is chapter 2. I don't know. He has them. They're named all over the place. But it is a little cumbersome for. Oh, you're good. I was about. That's slightly better. Sort of. Okay. He has a lot of examples in there, and I'll kind of go over the more shortened version of it. But it is really, really good, especially if you had to write out the whole equation, or if you
What?
is it cold?
It's not, I didn't put it in the fridge. It's still Dr. Pepper. That's not
They drinking it up.
I'm thirsty.
Yeah, well,
Well, the meeting's better than the more sober.
It's good enough. It's not warm. They know me. So anyway, it's really good, but I'll go over kind of an abridged today. Let's read the question. Second order differential equation and initial conditions for the terminal voltage of a scaled RLC network with a current controlled voltage source is given below. You don't need any of that. That is not important to the question. Don't think about it too much. You don't need it. What you need is basically just this. It's 5 minus Rm, and then the second derivative, v of t. 6 minus 3Rm, second derivative, or first derivative of Vt, and 2 minus Rm Vt is equal to 0. Let's keep reading. Rm is the trans resistance parameter. Okay, cool. Make use of this equation to do the following. Calculate the value for Rm that will produce a critically damped response, and calculate the value for the exponent P for the critically damped response. Okay. So, critically damped. Does anybody remember what critically damped means? So it is specifically when the discriminant of the quadratic is equal to 0, or the discriminant of the equation, otherwise known as the area under the quadratic. I'm going to write that down. And we'll call this. All right, that's the big picture. Who remembers the quadratic formula that you haven't used in years? Nope. B squared. So it's negative b plus or minus square root b squared minus 4ac over 2a. Correct. So this is the full quadratic equation. I recommend writing that on a cheat sheet so you don't forget what it is in the exam. What the discriminant is just this bit. So the disk, I saw for the previous video last semester and you replaced mine. Oh, no, that was already there. Equal to b squared minus 4ac. Yeah. I can't spell. It's discriminant. So yeah, b squared minus 4ac. So what is critically damped? Exactly. So discriminant equal to 0. Crit. So it looks like all we need to do, right, is use this, plug it into that, set it equal to 0, and solve for Rm. Right? We're just looking at the discriminant right now, because we just need to find Rm. So we're on A right now. We know the discriminant is equal to 0. So we can find what Rm is using that equation. One unknown. So now, the thing that I always forget is which is A and which is C. Is A the first one or the last one? Is A the okay.
It's not ABC. Yeah, it should be ABC. It's the highest, right?
Oh,
yes.
A, yeah.
Yes.
A equals to-
I'm thinking of later on, he labels them A1, 2, and 3, and not A1, 2, and 3.
Oh, it's like A squared plus A plus B.
Yeah, or yeah,
Yeah, this is, so that is A and C. There's, oh, yeah, I'm sorry. That wasn't clear.
Now,
you were recording.
I thought it was like.
Yeah, no, you are exactly correct. It is A, B, C. There's something else that's in another step of writing out the full equation that has to do with A1, A2, and A3. And A1 is not that one. A1 is this, and A3 is that. Ignore everything I just said, though. You don't need to know that for the exam.
If you order derivative.
It always got me. But let's just set that equal to 0 and solve it. So we have b squared. So we have 6 minus 3rm squared minus,
B squared. For A, 3 needs to be 1.
so
There's a constant.
yes, you don't actually have to do that. I figured out. I thought you did. I thought you did have to do that. You do not. I thought that you had to normalize when you found it, but I was incorrect, and so that makes it easier. So A is 5 minus RM times 2 minus R. So then what we're going to do solve.
Oh, intercalculated.
Yes, comma, RM. Yes,
Oh, so.
that is exactly what we are going to type into the calculator, and it will give us the answer for us. Because that is gross. That's gross algebra. Do it. Let's do solve. 0 is equal to 6 minus 3R. I'm just going to do R if that's okay with y'all. 5 minus R. R, comma,
The normalizing thing, what would that be helpful for? Or will we actually, because you said he might change his mind about something, so.
you shouldn't have to normalize it. So you put the comma there where you say that's what you're solving for. In the calculator, that's literally what you type. You do a comma to tell it solve for this or that. That's a lot of fours, sorry. Because it's squared. So here you have two possible values. Now you need to figure out which is bounded and which is unbounded. Because they're two different signs. Actually, they're not two different signs. We're going to plug them in and see that the P is going to be negative and the P should not be negative. Other way around. It should be negative. It should not be positive. Okay, what is P? So to find the p, we are going to, was this not on your homework 4?
Oh, it was like.
It wasn't counted for a grade.
Right. It got look like the last day.
We didn't go over it before the last exam. Like last exam, we didn't have enough time to do this.
Okay. Cool. So to find p, what you do is you're literally just going to plug in your values here. And plug RM in, and then solve the quadratic. Does that make sense?
Just plug both numbers back in.
So yeah, -4, 4, 2. So now we're gonna 0.4.
Is that what popped up in the calculator, 0.4 or 2? Yeah.
Yeah. So now we're gonna plug these values in to here and see what we get. So we're gonna do for the way I'm gonna do this. I'm just trying to decide how I want to do it in the calculator. If I want to do set values for A, B, and C. Do we want to do 2 or 0.4 first? 0.4. Okay. Negative 0.4. So we're going to do negative 6 minus 3 times negative 0.4. That's what it was. What's that? It's 0. So we're going to plug it back in there. Do we have to do plus or minus? Nope. So we just have to do just negative b over 2a. 2 times is negative. So, can y'all see that? The negative 0.66666. And then we're going to do the same thing with 2, right? And then I'm just going to show you why we're doing this. That doesn't seem right.
What you said this to me again? Bring the RN into what?
I'm putting 2 in,
As part of the equation? The original.
like the actual quadratic. Did we do this right?
This one, negative 0.4, if you have it on June. In the settings where it's always like 9.3 or something. Instead of encapsulated, we did it by plus 0.4. So it's like originally minus, so plus is another. The R is negative 0.4, so you have to change the value. It wasn't affected.
Pretty sure I did it right.
Next one, never be zero, or?
I just don't think that's the right answer. That, like, I looked at this beforehand, and I don't remember that being the answer, which is why I'm questioning it. I don't think it's that it can't be zero. And to answer your question on there, you do use the full quadratic. We are still using the full quadratic, but we defined critically damped as the discriminant being equal to zero. And so we already know that b squared minus 4ac for both of those values is equal to zero. So that simplifies down to just negative b over 2a.
Oh, but I guess like for, that's true, but like, how do we know which one's right though? I mean,
So usually one of them is positive and one of them is negative. You want the negative answer because so, and you want that because it's in the exponent. So
oh, because like, yeah, we'll make it smaller over time, is that why we want to make this exponent?
yes. So you're looking, and I was gonna pull up chapter Z1. Because it's basically also, did that make sense online? Like K something to the P. It's like a V to the P, but what is this? KE to the P. Critically damped, we want to converge to zero, right? E to a negative number is going to converge to zero, and E to a positive number is going to converge to infinity, right? And so for the exponent P, we want it to always be a negative number. Does that make sense? Okay, cool. Yeah, KE to the P. Oh, I had it on my other computer. I was like, where are all of the documents that I had open? Could not figure it out. Oh no, okay, we did do it right. Cool. Yeah, so we didn't even realize we were doing it, or maybe y'all did, but we solved A. We also just solved B. We just solved for the P, but we had to do that. We had to solve for P to figure out which RM value we were using.
So we did. Wait,
So for part A, we would have to know which RM is like the true one.
to the solve
We
part.
can't just put both and be like, that's the RM.
Because it's only one of them. They're not two critically damped values. There's only one.
You test to, like, do it by plugging in A and B for, and you go into A, or is it like?
So you plug RM into this and then plug that into here. So here I can
Unless it's negative, meaning it's the graphs that be trending downward.
Yeah.
Everybody.
We're plugging anything through. like the derivatives and B, like derivative BT or derivative square BT. Like the B squared, the derivative squared, the BT, everything after that.
Mm, no, so all this is, I can just, all this is, that was the worst brace ever, is just X. This whole thing is X squared. And this is X, is essentially 1.
Not even be-
Solve for like when Yankee was like 1 or something. What was it again?
So that is to do your like
Like normally.
there's underdamped, underdamped and overdamped, but then you have to and this is someone asked this earlier, if you have to write the full expression. So this is kind of where you would have to write the full expression. So let's do, what value did you get for P? We got negative 0.6666. So remember that K that I mentioned? You have to use the initial conditions to find the K. That. Trying to find it in chapter Z1. That's what I'm doing right now.
Now.
You
You can, but you shouldn't. It's not advised.
What's Fernando in here?
You, sorry, how did you get here?
So we literally plugged in. So I was writing it out. So I'll get back to what you need those for in a second. We're going to plug in RM is equal to negative 0.4 to our original quadratic, right? So, and then what I'm doing is I'm plugging in to the quadratic formula. So this is negative B. I'll even write plus or minus the square root of 0 over 2 times 5 minus negative. That is what you do for P.
It's, it's 0 not true because it's quickly down.
It's 0 because it's critically damped.
Yeah.
Is that what you said? Yes. Because that is how we solved for RM, is we set this value equal to 0. 2 minus square root of 0 over 2 times minus 2. Okay.
Is B6 minus 3 times 3?
Minus 3.
That bottom one starts plus. There's no negative on the bottom.
And so that we got negative, so that's bounded. So P is equal to that, and RM is equal to that. And that's the problem.
Decided that negative 4 is the right one because, P has to be negative.
Yes. Because it's bounded.
So keep on decimals, or could we say just negative 2/3?
That's fine. Generally, decimals are preferred because all of the solutions are in decibels. And so it makes it easier on the TAs to not have to plug in the fraction. I think they usually will, but it's just another thing to have to do. So, okay, here we go. Here we see the homogeneous solution for the critically damped is this, K1 plus K2T e to the PT. So there was more, but it's basically K plus e to the PT. We want that to be bounded. That's why it needs to be negative, because bounded means it decreases to 0. To find K1 and K2, you start doing this stuff. So the X of 0 is V of 0. So he actually gives you that. You don't have to do this. This was just if you were curious why they gave you initial conditions. So V of 0 is equal to -1. So specifically for critically damped, K1 is equal to 1 because of that. And then to find K2, you see that it's the derivative T of X of T, where T is equal to 0, is equal to P times K1 plus K2. He gives you that. And you know now K1, you know P, and you know the derivative, so you can find K2. So if you had to write out the whole thing, that's how you would do it. For critically damped, it's a lot simpler than the other ones.
Like a question, just like this, except it's not critically damped, something else, like
It'll be critically damped.
it's always critically damped.
For this exam,
Yeah, yeah.
it's going to be critically damped.
Okay.
These? Okay. So I have a complex emittance and I have a switch. Have you seen this switch problem before? The specifics, I didn't go over this in the review.
Whatever problem, but it's not.
Was it?
Remember, it was like the middle switch was really messy.
Yeah.
I think it might be slightly different. Because this was from an old exam, and I don't think he gave a homework problem on an exam. Tries not to do that. So do we want to do switch or do we want to do complex emittance? I was going to say, which do you feel worse about?
I never heard those second words.
Complex emittance y'all feel worse about? Oh, well, let's do that one because that's the easier one. And so
You know how to do both?
we do. I just know that people might have class and they might. I said technically until 5 and it's 4:30. And so I want to try to do what is more helpful sooner in case people like I'll go through both of them, but just first. Okay. I'm pretty sure you haven't seen this one. All of the semesters have melded together in my head. So let's read it. The network shown is a scaled RLC network, 0 initial conditions. That just means it's steady and happy. Source driving the network is an AC voltage generator with a frequency of 1 radians per second. So it's already in omega. It's already omega. The time domain expression for the source is written as EG of t is equal to 5 volts cosine t. generate the sinusoidal steady state expression for the voltage V3 of t in the time domain format of said equation, where V3m is the magnitude of V3 and V is its phase angle in degrees. And we have a big friendly mesh or circuit that looks a whole lot like MAME, right? So
The equals something over the.
So if you see for this exam more than one inductor or capacitor, then you're going to think complex admittance and try to see if you can solve it via MAME or NAME. V3. Yeah. So sorry. There's a couple different places that we could start. Excuse me. But identifying that this is a MAME problem is where I would start. There are two loops. You have voltage sources and you have resistors in ohms. That looks like MAME, right? And that is contrary. I will show you kind of what the opposite looks like. Do you remember how we saw here, everything was in current sources. We had G's and we had nodes clearly labeled. We think NAME. But here, we think MAME. So what do we think of when we think of MAME? Yes. Oh, mesh. We're going to do 1 and 2. Cool. Do we think impedance or admittance? Let me rephrase. Do we think of resistors or, okay, which is resistance? Impedance. Good. So we want impedance. We have our mesh loops. So we need everything in voltage sources. What'd you say? Yes. Yeah, because we have loops. We don't have a bunch of things in parallel with nodes. We have big things in series. Voltage sources, and we need to write equations in terms of mesh currents. So first thing that we're going to do is we're going to write out our impedances. Actually, this is not the first thing. The third thing, because I already said the other two first things. So the next thing we're going to do is write the impedances. So y'all can see that it's R1, L2, C3, L4, and R5. Are you good with me doing Z1 through 5 corresponding? Or do you want me to do ZL2? Do you see 1 through 5? Sweet. Okay. So let's just start Z1, super easy. What's Z1? 1. Z2. 2, 3. Not quite. So we need to convert the 3 henries into complex form. So what is the equation for impedance of an inductor? So yes. So that is for L, it is J omega L. This is for impedance. And for C, it's 1 over J omega C. Or negative J over omega C. Those are the same. Because 1 over J is equal to negative J. And then side note, admittance equal to 1 over Z. So L is equal to 1 over J Y L equal 1 over J omega L Y C equal to J omega C. What's omega?
It's 1, 3.
It's 2 pi f. That's where that came from. But it gave us frequency, which we normally think f, but it says specifically 1 radians a second. Because it says radians a second, we know that that is angular frequency. But if he just says normally frequency, the frequency is like hertz. We need to convert that to radians, and that's where 2 pi f comes from. So omega is equal to 1 for this. But this is good to know for name. So that is important. It's 1 over your Z values, but yeah, admittance. Sorry, that's a word. Admittance is a word. Oh, it's 1D too. Oh, I always forget that. We're gonna go with admit. Because source is an AC voltage generator with a frequency of 1 radians per second.
Okay.
Yes, you're good. You're good. And that is the unit for angular frequency is radians per second, which is basically how all of thermal works. If they give you the unit, that's how you figure out what the thing is, which is frustrating, and I don't like thermal. Yeah.
Oh, I might not the class, right? You think?
Thermal engineer, yeah. Yeah, I'm in there right now. But anyway, Z2, so J omega L. So it is actually just 3J. Because omega is equal to 1. This problem is relatively simple because of that. 1 ohm. So this is number 1, this is number 2, number 3, 4, 5. See, 3 is equal to, let's see, 1 over J omega C. So 1 over 1 times 1 is negative J.
1/2 times. Oh, that was for.
No, so this is the inductor. So it's J times omega, which is 1 times 3 henries. So it's going to be 3J. Or we're going to come over here. That's inductor 4. So now it's just J omega, which is 1 times 0.5. So that's 0.5 J. And Z5 is equal to 4 because it's resistance. Cool.
Good for each,
Okay, only thing left to do is we need to convert this into polar form. You could also do it in J, but polar is the easiest to take from sine. Because I'll do it here. This is equal to A phase angle V, which would be V3M phase angle V3. And that's just kind of the sinusoid to polar definition. Technically, it's supposed to either be cosine or sine, and you're supposed to do a phase offset, but because we're starting in cosine and ending in cosine, it doesn't matter. If we started in sine and ended in sine, it also doesn't matter. So don't worry about doing a phase shift. So what is this in polar? Yep, it's just 5. It's technically 5, phase angle 0, which is equal to 5. So now we have a 2x2 mesh and we know how to do that. We're good at main, right? Let's do main. Okay, what's in our, what do we got in number 1? 1 plus,
Oh, 1 plus 3, 1 plus 3.
1 plus 3j minus j. So 1, are you good with me just writing 1 plus 2j, or do you want me to write the whole thing out? Okay. All good. That's why I ask.
What's the rest of the?
Because you see all 3 of these elements, and then we have all 3 of these listed out. And so this guy, this guy, this guy. 1, 2, 3, 1, 2, 3. What's shared between the 2? Yes. Yep. And then last one. That's it. And then I am 1, I am 2. Technically, you could have that be mesh 1 and that be mesh 2, but don't do that. Just think about how all of your other problems have been. It always goes from left to right. Same if he doesn't give you the nodes, it goes from left to right. So what's this equal to? EG, are you good with me writing EG equal to 5? Or do you want me to write EG? Okay. EG, what else? So that can be plus or minus. RM times I2 plus 4. And then in the other one, it's just negative that, right? Now we need I2 and I4. Where are I2 and I4? I2, got I4. So again, we think back. This is MAME. We're writing them in terms of mesh currents, and we're looking for currents. So we don't have to write an equation. If it were the other way around, we would. Just remember current in terms of current, voltage in terms of voltage. I'm drilling it in because you can't say that current is equal to voltage. I've seen it too many times. I believe in y'all. But so current. What is the current I2? So it's just equal to IM1. What about I4? Yep. This one's pretty easy. So we're gonna go ahead and separate this out.
Did it include RM?
We plug in the RM. So it'll be EG0, do that, and then RM is 2. It's going to be 2 times IM1 plus IM2 negative 2 times IM1 plus IM2. Perfect. So now let's write out the 2x2 matrix. Not bad. What is it going to be? Okay, so now let's condense. So 1 plus 3j minus 2j, so that's 2j minus, or we'll just write all of it out. So then we have j minus 2, j plus 2, we have negative j plus 0.5, j plus 4 plus 2. Right? We tracking? We just writing?
Obviously, I'm just thinking if it was right.
Ah, yeah. And then I'll just simplify that out. That should be negative 1 plus 2j.
Are you the thing you're subtracting, you mean?
Oh, I'm just simplifying.
How do you get the 2, and everything?
How do I go from here to here?
Yeah.
Okay. So this is me just factoring out, because remember, we want to subtract over there. We need to make this side look like that. So we want a 2 by 2 times our IM. Matrix multiplication says that this side is IM1, and this is IM2. So we say, what's the coefficient for IM1 on this row? How many IM1s on that row? And we see that there's 2 IM1s, right? And then here, there are how many IM2s? We multiply that out, and we have 2 IM2s. Same down here, we have negative 2 IM1, negative 2 IM2. Does that make sense? Okay, cool. And then just subtracted that over. So now we just plug it in the calculator. I will go over how we get that. Now, J is not J. It's not I either. It is funky little special I that you get to with the pi symbol at the bottom of the calculator. That's how we get to I. And then we're just going to do the exact same of REF. Okay, 1 plus 2 I. 2 5. A plus 2. Just let me know if this is what you got.
Do we, in our answer when we're writing it out, do we have to include the 1 0 0 1, like, for the matrix?
No.
Does it matter?
No.
AG was supposed to be 5 or something. Yeah, it's fine.
Did I do 4?
I'm just wondering if that.
How do you get to show that angular? Over version?
Okay, yeah. So right now I have my calculator in polar, but regardless of where you have it, you can go to menu, number, because complex numbers, and then complex number tools, which is 9. And then you can either convert to polar or convert to rectangular. And so I had mine in polar, but if I wanted to convert to rectangular, I can just do answer We'll go answer rectangular, and it'll give me what the rectangular is. Same thing with polar. But let me know if anybody gets this. I don't want to run away with a calculator error and make. Same thing.
Yeah.
Okay, cool. Then we generally agree.
When you have I, it's polar, but when I have the angle, it's rectangular. Which should be,
Whenever it has the phase angle, it's in polar.
okay,
Then I is rectangular. So sort of. It matters because the question said generate the expression in the cosine. So we aren't quite there, but our final answer needs to be like that, which we get from polar. So the issue is, oh my gosh, auto dim, that's what I want. Sorry.
That's where the 5 and 0 came from, but there's review.
Yeah. So our EG was 5. And so there wasn't an independent source in the mesh 2. The only mesh independent source in mesh 1 is EG, which in polar 5 phase angle 0, which is just 5. It's that.
What if EGT had a phase angle? How would that change?
If it had a phase angle, then that would go in the phase angle.
So it would be the same thing, but the
Would
calculator.
make the matrix map out.
Correct. Correct. I think I'm understanding.
Like, yeah, like, it wouldn't be 5 phase angle something inside of our matrix when we're putting in our calculator.
No, it would. So if it was,
5 phase angle 30 or something.
Yeah. So if it was 5 cosine of, then it would be 5 phase angle 30.
But that's all right.
Yeah, that would go straight into the matrix. And we would do that. You have to write parentheses around them, otherwise the calculator freaks out. So I'm just doing parentheses around it. And then you can do control book, right? And then we see a little phase angle guy. And so control book, phase angle 30. And then we would get that. And it changes the entire answer, which makes sense. Then I'm just going to get rid of that. The only thing is, did it ask for IM1 and IM2? No, it did not. It asked for V3. So number 1, do we have voltage right now? No, we do not. We need to calculate the voltage. Number 2, is just one of those currents flowing through V3? Nope. So let's put all that together. Let's V3, just write it like it would be a normal voltage. V3 is going to be equal to R, right? So, do we know the resistance? It's negative J. So V3 is going to be negative J times the current. So it's plus and minus. And so we are going to try to make the arrows line up with that. So remember, this one is going to go that way. 2 is going that way. Which of these two is in line with the voltage V3? M2?
Yeah, not one.
Yes. So, so during MAME, we ignore passive sign convention, but then when we write these, we're coming back where plus to minus is positive, and current flows in a positive direction from plus to minus. So that is in the correct direction. And then IM2 is in the opposite direction. And so down here, it's going to be IM1 minus IM2. V3 is equal to negative J times IM1 minus IM2. Now, we can either take the polar versions of them and do that, but the rectangular versions are actually kind of easier. They're prettier, not easier in this specific circumstance. But regardless, which one do you want to use? Rectangular or polar? Okay, cool. So we need IM1, which is negative 0.2 minus 2.4 J minus negative 0.4 plus 0.8 J. Oops, negative J. And let me know if y'all get that.
For what is it? Negative J times the 2.4 minus 894 to the power negative 3.
So we're doing IM1, which is this whole value, minus IM2, which is this whole thing.
Hmm.
So we're doing both the real and the imaginary part. Which is also the same as negative 0.2 minus negative 0.4 and negative 2.4 J minus 0.8 J. Which I'll prove that that is correct. So that would be 0.2 minus 3.2 J, right? Negative. Same thing.
Oh, the rectangular.
So I just did that in my head. I did, okay, negative 0.2 minus negative 0.4. Okay, that equals 0.2. Negative 2.4 minus 0.8, which is these two, equal to negative 3.2, and then multiply that times negative j. So. How do y'all feel about this?
Did you say plus 800? Negative 3J?
Yes. So now just remember the difference between MAME and NAME. Did y'all eventually get complex admittance homework problems?
I think maybe there are some problems with the problem set 5, but that one was in a homework, it was just like a review.
Are they in problem set 5?
No,
Okay,
no. Oh, there's a couple of up problems at the,
Okay, and the second order, yeah, stuff.
okay.
when you plug the thing in J, did you put anything J for, like on B3? 0.2, yeah. So I'm one.
What? Sorry.
So, I am 1.2 and then I am 2.
No, sorry. This was me doing the subtraction in my head. This was me, I said, okay, I'm gonna do both of the real parts subtracted and then both of the imaginary parts subtracted. And I did that in my head and then multiplied it by negative j. That was me skipping steps. If that was confusing, then ignore it.
How do you convert it to the, angle level?
I'm gonna go menu, 2, number, complex number tools, 9, convert to polar or rectangular. So if I wanted to convert to rectangular, it would be that.
Four?
Yeah.
Like what I need to use.
Okay, alright. I'm not getting the angle symbol. Yeah, usually,
Are you getting E to the J?
yeah.
Okay, so you're gonna want to go into settings. You are probably in radians. At the top, does it say radians?
Yeah.
Okay, that is super duper important. Make sure your calculator is in degrees. If you're renting it out from IEEE, it will probably be in radians.
Oh, make sure it's.
Make sure it's already.
Put it in degrees.
Or.
And you can remember that because the phase angles are in degrees, so degrees.
For the final answer to the expression, you take the real, part of the E3 and have it into the amplitude.
Mhm.
For example, for example,
Exactly. So I should probably write out the answer. V3 is equal to 3.206. And then back up here, V3 amplitude cosine of T. So back here, cosine of T. And our phase angle is negative, so it's going to be T minus 176.424. That is our final answer. But yeah, just work out. I can probably send out on Discord one of the a problem set with complex admittance problems. Just so you have some extra problem sets to work through. I can't believe he didn't put complex admittance on the problem set. That's honestly crazy.
But it's the same kind of complex admittance like the last review.
I'm sure that means like you won't have another testing.
No, he said we have 4 questions, do the 40 questions on this stuff. But there's reviews, last semester, she was like, over complex. I don't know if you need it.
Oh, right, just the compliment stuff.
No, this is,
Yeah. Oh, okay, yeah. I forgot. And then I'm not worried, I'm just putting that like.
switch problem.
You said you studied the test, right, for the exam?
Wait, is it?
I don't know, these four topics, she's not comprehensive.
Sometimes complicated.
I mean, you're not reading everything, like, I don't.
There's actually really not that much from the first exam.
That's true.
It's like voltage current.
Yeah, it was like out of it, they were looking over this.
Yeah.
He honestly normally puts more in from the first exam, but he didn't this semester. I guess y'all just did too good on the first exam, so.
Second one, I got a 20.
Oh, really?
Yeah.
Like, what are you?
So
I mean,
They got the sort of which one.
y'all are gonna be okay.
I just hope that, like, cause like for that second exam, we just like Norton's in here, but on the actual evidence, it's like the reverse of everything we learned in
I
the
got
year.
75.
Just like threw me still up there, I think I did not do well on that.
Yeah.
Okay.
You gotta, and same goes for this one. I'm giving you Thevenin's, it might be Norton's.
So at least we have like the example from last.
Well, I basically 17 class.
Just the only difference between Thevenin's or Norton's is name and name.
Some words that names. But also just studying it up, you know. it's
Okay.
hard.
Yeah. But do we want to do a switch problem before we go?
One more problem? Yeah. Cool.
Okay, let's do here. I'm gonna. I wrote this really big, so.
I was just doing in single home, and I was like, what am I doing?
Okay. RC network. Time is equal to 0, switch 1 is open, so it starts closed. Using the values, you are asked to calculate the values for the capacitor voltage, capacitor current, and network time constant, and fill out table 3. And then apply these values and write the full time domain expression for V of t found from the solution, yada, yada, yada. So first thing we should see is that it is a capacitor problem. We can fill in zeros. Did the TA count stuff wrong with zeros?
I've got like that. I'm good at that.
Could we talk to the TA to see if he can give us?
Someone's talking to them, and I think that they will. Yeah, you can pick them up. Someone asked me a question about it, and I think that they're getting it sorted out. I think that part of it was graded like a teensy bit wrong. It's only like 2 points, but yeah. So I just like he might change the grades, but I'm just like fair warning. It's not like it's gonna be like a ton. It's like 2 points. But anyway, capacitor. After a long time, what happens? It is an open circuit. After long time. Open. Is there any current flowing through an open circuit? No. Oop. Right. Cool. 2 out of 7.
After like it resists changes in current, but not voltage.
Yep.
Is it only?
No. Other way around. It resists change in voltage.
Voltage, not current.
Correct.
Is it only like an open circuit if it's been closed for a long time or open for a long time?
Either.
Either.
Just after a long, because the switch is what's closed and open. The capacitor doesn't open or close. So the circuit, after the circuit has been steady for a long period of time, the capacitor acts as an open.
Right.
So regardless of, because the switch might be somewhere else in the universe. But we can immediately do that. Let's just start it off. So let's redraw it with the switch closed, because that's time is equal to 0 minus, right? So we're gonna go ahead. Mhm. Oh, I regret doing this. Dang it. No, like
Small one.
we're just not gonna do one of the parts because it's a really, really long derivation. And if you want to go do it, you can go do it, but it shouldn't be that hard on the exam. Oh, you'll see when we get there. You'll see when we get there. Okay, so when it's closed, does this exist? When it's closed?
Oh.
Short circuit. So this goes away. So we just have source. Open.
Voltage source just out of the one.
It shorts out. There can't be a voltage drop over a wire. And so that's not going to be doing anything. So technically, this is more of a terminal than a capacitor because this isn't open right now. But what we're trying to find right now is the voltage at 0 minus, and this is the circuit at 0 minus. So how are we going to find the voltage from here to here? Yeah.
Main.
Main?
Okay, okay, should be something. Okay.
Would not be the JG times the R.
Not quite. So I'm gonna redraw this.
This parallel with the pretty big.
Wait, resistor. Oh, these are these.
So
But we wouldn't want to change the node. But
correct. But the first thing we see, so we're looking for this positive place right here. So we want the voltage at this node, right? Is that voltage any different from this node? Mm-mm. Here. So this is actually just ground, which is funky. So I think you said it. It is pretty much a voltage divider. So we just kind of want, not kind of, we want to know the voltage here and we want to know the voltage here. So let's redraw this. And I'm just gonna kind of redraw it and you're gonna tell me if it looks okay. So what can we do from here? How would you do that? So remember, this is a current source. You either need to convert that to a current source, to a voltage source and a resistor, or like do a current divider. Which would you rather do? Cool, let's convert it to a voltage source and a resistor. So 12 milliamps and 1K, 1.2 volts, right? So it's always, and I'll go over that in a second. I want to finish this first. 6K, K, 0.2. So now we can pretty easily find the voltage over the 3K. What does that equal?
Seven over 3 plus 7. Times
Mm.
7 and 1.
No, it should be 3 over 10.
Oh, 3 over 10.
I always literally just find the current and then multiply it, but voltage divider is probably the right way to do it. It should be 1.2, right? I'm not. You're making me question myself. Oh, it's 12, isn't it? Is it 12?
So
It's 12. Whoa. There we go. 12 volts. Okay, so then the voltage there to there, gonna be 12 times 3 over 10. But 3.6. So voltage is 3.6. Nope. No. I'm giving you all a hard time. Look at the polarity. I'm sorry. I'm sorry. I'm being.
I thought it was like, look, this is not it, this is the step to get to the next step. Get to the next step.
No, it's just negative because 3.6 is that way, and we're looking for the reverse of that. Yeah. So, because this is I don't grade. I can't talk about how it's going to be graded. That's- yeah, but I can't promise that's how they're going to grade now. But so we have negative 3.6 volts. Can we do anything else? What can we do? Precisely. They are because, and you said it earlier, resist change in voltage. Boom.
Oh, I thought it'd be like 0 minus 0 plus because they're both long time. And that's why it's short.
No, because they're both after a long time, but the voltage supplied in the circuit is completely different. If you think about it like that. So the voltage over time is going to change. But since it resists change in voltage, because 0 minus and 0 are essentially the exact same time. So the voltage change is, again, essentially zero.
That only applies to voltage, right? Voltage zero plus, or voltage zero equals voltage zero minus only.
Correct. But for an inductor, it is the exact same, except these two are flipped. It resists change in current. And after a long time, there's no voltage. But, yeah. So, we're gonna do times equal to t infinity next. And we're gonna not do current yet. So let's draw out the circuit again. Like I said, I am not a huge person on like typically. No, you're good. You're good. Drawing out every single time. And I think I've said this before. Like whenever I'm doing resistor combinations, I do not draw it out every single time. On switch problems, genuinely. Basically draw it every time unless you can use the same drawing twice. These get funky on how they get reduced. And so I just recommend. So let's see, how do we want to do this? Current and then sum them in parallel.
Wait, yes.
Huh?
Your voltage and current source and add them together and voltage source, or,
Or like turn 9 volts into a current source,
and then add them and return it back into a voltage source.
add it to like 12 milliamps plus whatever we get from 9 volts,
Yeah,
and then turn that back into a battery.
yeah. Can you do that, or?
So
Just a quick question. If we use superposition?
Yes.
In this one?
Yeah.
And we didn't cover this in class.
no, we did not.
Here it is. Would you, if you were to use that, would you just, short, we calculated twice, right? You would short the voltage source and then find out what the use, name to solve that, and then, find the voltage across that, capacitor, and then the second time you go through it, you would open the current source and solve for the voltage, and then sum those two values.
Yeah, and that's how he does it in his solution. Also, we already solved for a shorted battery. And I think that's part of why he did it. He's in his head like just use superposition, but he doesn't teach that in class.
Right. Super. Never talked about it.
Yeah, which irks me a little. And
You're mentioning it kind of as a
Yeah.
test for linear and given class.
So I typically in my reviews try to not solve using superposition, even though in this situation it is the easiest way to solve it. We're gonna do a little bit of weirdness, but it should work. Okay, so y'all ready for a little bit of weirdness? Y'all remember E-shift?
Oh, no.
Okay.
Wait, so we're moving the 9 volt battery like up?
Mhm. Mm-hmm.
I remember E-shift now,
Like
but.
we can make 9 volts, it like, it becomes, it becomes 2 branches.
Oh, no, those parallel. I hated that one.
But, what if we do like open circuit short now? Then it's still just.
So it stays as an open circuit. And here, I'll show you, and I'm just gonna do this again of I'm just gonna redraw it.
Could you, like, or is the placement of the source and the 1K resistor, is it in a place where you can't turn it into you can't just turn it into a current source and then add it together?
Correct.
Uh,
Because this is on that same path. But the way I am writing it right now, you'll see that you can do that.
Oh, okay, I see. Is it because of the common ground? I think it's the node on the positive.
Yeah, it's right here. Because that splits off. Well, it's
Also, when it splits off, the middle part becomes a wire, and then we just move, we make that touch the very bottom.
so you get rid of the node. If you do that, you don't preserve that node. So how can you go back and find the voltage? In this weirdness way. You see how I did it? Okay. So what I did is I did E shift.
Oh, yeah, wait.
And so I pushed it up first
Yeah.
and then I pulled this down. So it's the exact same thing I did here, except now on both of these branches, there's a battery. And so then this turns into and then we're gonna condense it down, right? And then condense, so what is it, 9 over 1K, so that's 9 milliamps, right? So 9 plus 12, because we're going in the same direction. 21. So you have 21. Mm-hmm. 21 amps. Okay, and then I'm just gonna go ahead and convert that back to a battery before I redraw it again. So then so so this way. Now this technically isn't connected. This technically does not exist. So we can do a voltage divider here again to find what the voltage from here to here is. And then we take that and we know that that's going to equal to the voltage over the capacitor plus the 9 volts. And that's how you have to work to not get rid of the node. So what is that? 21 times 3 over 10. 6.3.
Not the other resource like the 9 volt.
So that was up here and that got converted into another current source. So it's not connected.
So that's what you were saying, didn't technically.
Mhm.
Gotcha. Is that because it's a split off?
Because the capacitor acts as an open circuit.
Right.
So it's not connected, but because that voltage source is there, you can't just say it's the same voltage as the 3K. So what sign did we flip?
Find the polarity on the belt, battery.
So here, let me see if this answers your question. So this is the polarity of the capacitor voltage. Where I am right now, I did this plus and minus because that's the voltage divider we're going to calculate for.
Yeah.
So that is this voltage here, 21 times 3/10, which is equal to 6.3. So positive 6.3.
So what are the poles split?
He said, why did the polarity flip on the outside with 3K resistors and that the 21-volt battery, I believe, no? That the plus is.
Yeah,
going
the
around.
inside's minus and plus, and that's a plus and minus, but not down.
And the last diagram, where the 3K resistors,
Uh-huh.
he's asking why I said plus minus.
So I did plus minus because that's how we're solving for the voltage divider. So that's like in the circuit, like current is going to be flowing this way, and the voltage drop is going to be like that, going to be like that, going to be like that. And so whenever we solve the voltage divider, we're solving for plus minus this voltage, which is going to be 6.3 volts.
How come they didn't apply to it?
It did. Yes. That's how we got this, what we solved for, 3.6 was plus minus this way. But the capacitor voltage that we were looking for was this polarity. This is cap B.
So you had minus 6.3 plus, then you'd have that 9.
Wait, you would technically like subtract the 9 because you're saying um yeah, you're gonna subtract 6.3 from 9, basically. Because you want to see, okay, this is 9 volts. But we see that it wants this voltage here. 6.3 minus something plus 0.9 is equal to 0. No, sorry. No, 6.3 plus something minus 9 is equal to 0. Mhm.
I guess like earlier, when you were talking about how 9 volts doesn't exist. So I kind of was writing the previous text while the step we're on right now is kind of going on.
Period.
So. And I'm just like, a little-
No, you're good. I think I see where your head is at. So this does not exist in the way that this 9 volts is not providing any power to the circuit. However, due to KVL, the voltage drop from this point to this point needs to be the same as the voltage drop from this point to this point. Exactly. And we are trying to solve for this capacitor voltage. And so because these two things should be and will be equivalent in voltage, even though it's not providing any power, we can see equivalently what the voltage is. That makes sense?
But why would it equal 0? Wouldn't you do like 9 volts
Sorry.
plus capacitor voltage equals 6.3? Or no?
Yeah, you would. But I did 0 because this is ground. That's all. But yeah, the long story short, it's 9 minus 6.3 equal to 2.7. Did you do superposition?
No.
Okay, cool. You're good. That is the probably smarter way, but this is technically the way that you have learned and had homework problems over.
I have one question, but if you were calculating, tau.
Yes.
For that capacitor, can you show how you would find the equivalent resistor
Yes.
value? That's been the biggest challenge whenever the resistor is in random or the random.
Yes, and I will do that next.
6.3 or 6.7?
2.7. And that is why we had to keep this 9 volts there. Because 6.3 is the voltage drop over the 3K, which is not the same as the capacitor voltage. This is 2.7. So now we are to the point that I don't want to do, which is the current. So I'm going to tell you how you would do it though, and then we're not going to do it for this problem because it's going to take even longer than what we just did. This was on the final for 2 semesters ago, and I am sorry for them. One person in the entire class got the current right, and I was very proud of him. But point is, what you do, you know what the voltage is at times equal to 0. It resists change in voltage. So what we do is we take this value and make it a voltage source and put that at the capacitor. So we take this and plug it in as voltage source. Which I think actually, now that I think about it, you can do the same E shift. And then you would have to find the total current and then do a current divider, which is gross. But it is doable, but I want to just kind of continue. If you want to do it on your own time and ask me, did I do this right? Feel free. But what we would do is, instead of here, I'm just going to do it this one.
T0 the same circuit as T0 negative, right? That's like the short.
Yes. in this specific circuit. It's not always.
So you talking about whenever it's infinity, what time infinity, line for the better.
Oh.
At time infinity, when the voltage can after be negative 2.7 instead of normal 2.7.
Hold on, hold on. Are you in the back asking about this or
Back.
this? Okay,
Where you put the battery running faster when that's the facing the order.
so it's because it's negative 3.6.
Okay.
Sorry, that's why I was pointing at the negative.
Alright.
I wasn't using my words, I apologize. You, it should not be, because it's at 6.3 here. And this is why I kind of did the down to 0. Because if we start here and we come down and we hit a negative, we're going to add voltage, right? Because passive sign convention. We have 6.3 and then we go through a negative terminal. And so we add 2.7, right? Let's just assume we know it's 2.7. And then we go through the plus, and so we subtract 9. And so then we get to ground, which has to equal 0, right? And so that is how we get from 6.3 to 0. Does that make sense? Cool. And then from here, what we need to find is the current pointing. Very importantly, we need to find the current in that direction. It tells us which direction, so it wants to find the current there. We can do that kind of using E-shift. That's probably the easiest way to do it, because you can't do MAME and you can't do name because you have voltage and current sources in the same circuit. Like I said, E-shift is kind of what works. And the way that you would see that is anytime you see a junction like this in Russell's class, E-shift is honestly a great thing. I think someone I-shifted, which was pretty impressive on the exam, which also worked. No, it's shifting the current source, but
Oh.
we're off in the weeds. And if y'all are okay, I'm gonna proceed on to finding tau.
Yeah.
Just remember that.
I'm just checking in on, how far y'all are at. I think we sure, P0 is the circuit where it's, you have those two more sources, like one at the bottom and.
Yes, yeah. So this is where your current is actually gonna have a value. This is right after the switches. And when the battery, the capacitor is resisting change in voltage and acting like a battery. Wordy. The next thing, and there's so define tau. What's the equation for tau? RC, beautiful. RC. That means that we need to find the equivalent resistance. How do we do that?
And voltage source into the open. Opposite direction? Oh, just like that.
But
Alright.
yes. However, only stipulation is that you are finding the equivalent resistance at these terminals. So you are imagining yourself as the capacitor. You are looking into the circuit from those terminals, and you are seeing what the resistance is that the capacitor is seeing. It sounds kind of silly, but it's like the eyes are looking there. So you're never gonna have the point from A to B be connected. Those are, I say to do it like off like a resistor problem and draw the terminals, draw them like A's and B's. Draw it like you have A, which is positive, and you have B, which is negative. And then redraw the circuit, the resistors looking that way. And then it gets way easier looking. It's just tricky to get there sometimes. And it is probably the hardest part of most of these problems. There's one on your homework set that is, it's a brutal one. So like everyone said, we're opening the current sources and closing the battery. The other thing is you are finding tau with the circuit after the switch switches. So you are using the circuit of time 0 and to infinity. So those are the two important things. However, in this particular situation, it doesn't matter because it changed from a short circuit to a battery, which we're then shorting again to find the resistance. Moot point on this problem, but alas. So what we're gonna do is really just look at the nodes. And I've said this before, and I probably said this at the last review too, but nodally is the best way to look at it, in my opinion. Because you see here, and we even drew it up here. We're looking at these terminals. We can see right here. Yep. We can see right here that that is connected to the negative terminal, and that negative terminal is connected to both the 6K and the 3K.
Oh, and so.
Mm-hmm. And then we can go there and see, wait a second, the positive side is also connected to ground, which is also where the 3K is connected to. And so I wish that I had more space up there. I'm gonna draw it again. I'm just gonna draw it again. It's small. It's A and B. And it's actually a lot simpler than it is on some of them, but I'm gonna still go through the process. Like we can see pretty easily here what it is, right?
Right.
So, but we'll go through and we'll look at all the nodes. So we see that this is a node. We see that this whole thing is a node. Can y'all see what I'm doing here? That's a node, and that's a node. So technically those are just in series though, but we're gonna get there. So we see that does B connect, or sorry, does the 3K connect B straight to A? So we see that A to B is 3K. And then in parallel, let's go from A to B the other way. We see that A, and that's, what is that, the 1K? Okay. 6K. K goes to 1K, right? And then that's connected to the 6K, which is connected to B. And I wrote that too small, whatever. That's one wire. It's fine. So that's 1K, that's 6K. Now that looks like resistor problems that you've done.
So you can do this with. Right?
Yep.
That was the one, that I could get at the very end of that.
Mhm.
Was taking that and transferring it to something like this.
Yeah. Does it kind of make sense looking at the nodes and,
Yeah,
okay, sweet.
yeah.
3 in parallel with 7, that sounds right.
Was it?
18 nanofarads.
What were we get rid of? What's the sources again?
So this is just looking at equivalent resistance. To find equivalent resistance, you turn all the sources off. That's kind of definition. That's how you find it. However, big however, and this is kind of just to know, this is not going to happen, but it did happen last semester. He put a dependent source in a switch problem, which was mean.
You can't get rid of it.
That was mean. No, you cannot turn off a dependent source to find equivalent resistance. So you had to keep the dependent source on and do a MAME to find equivalent resistance. Oh, well, poor kids last semester. Not like that, unless he changes it last minute.
And there will be no op amp.
Correct. There will not be op amps.
So
And
he doesn't print the test out like the point of.
yeah, pretty much.
Wow.
And he has also reprinted them before.
Sorry, guys, you're gonna be a little.
Up to how it feels in the morning.
It's more like night before, but yeah. He like gave me the problems and then he was like, you know what, Grace? I wanted to make it easier. I took off one of the problems, so it's only 3 problems. And then he changed the problems that were on there. And so it was the exact opposite of what I had told them to study.
That's what, this test for us, the second one.
No, it was like 2 tests ago. It was totally different.
Like 3 12 hours.
No, he planned for it to only be 3 problems.
Okay.
But anyway, that's what I got. Do y'all have any questions?
Gets the R times the.
Yeah, pretty much. R is equal to 2.1K time and tau is equal to 2.1K times 18 nanofarads, which is 7.8
Got 37.2, yeah.
milliseconds,
But
microseconds.
I have a question for you.
Oh.
So I remember there was one where it was like there was more steps to our TRC where it was like natural log of.
Yeah, so I jumped the gun. We need to write the full time domain expression.
Yeah.
That's important. Don't forget to do that. That's worth 13 points. Make sure the switch problems get you on that. Make sure you go back, like even just before the exam, look and see what it asked for. And on this one, you need to write the full time domain expression, but that leads me into what you were just talking about. So what is the time domain expression? VC of t, VC of t equal to yeah. 0 minus v infinity e to the negative t over tau, which is equal to 2.7 plus negative 3.6. Sorry, that's a 2. I write lines in my z's because my 2's look like z's. So negative 3.6 minus 2.7. Let's try it. So that is the expression. So the two other things that he can ask you for are the rise time, which is the best thing, because what's the equation for the rise time? It's tau ln of 9.
That's the one. Go.
It's the best equation. It's just a constant times tau. So if he asks you for rise time, just tau ln of 9. And then the other one is he will frequently ask you, what is the time at which the voltage is equal to 0? And this one, that is a valid question because it goes from negative to positive. So what you do is you plug in 0 here for this whole thing, not at t. You say, okay, just pretend like that's the same paper. 0 is equal to 2.7 plus like whatever, negative 3.6, 2.7 e to the negative t over 8. And then you say solve comma t. And that will give you the time at which voltage is equal to 0. And then if he wouldn't give that. If for some reason you needed to find the voltage at a time, instead you would plug it in here. You would plug the time in there. But that's not really what he asks for. Okay. So, sound good, y'all?
Will you post those admitting problems and solutions in the Discord?
Yes. I will post problems and then I will post, if you DM me, I will give you the solutions and y'all can have them. I don't want to post the solutions to a homework in the general Discord chat. Yes.
Could you repeat what the steps were for I-4 like finding that? Or the current one?
Okay, yeah. So
That we can do.
you're good. To find the I, all we're going to do is plug in this voltage into here. So after the switch switches, we're going to plug this voltage in here. We find 3.69.
That would be like a mesh thing, but.
That it just completely depends. So that completely depends on how the circuit is. That completely depends on where it is. Like I said, this was a really hard problem and I didn't mean to grab it. In the fact that it's gross to solve for current. If you want to try it, I can tell you if it's the right answer.
I'd probably Like, if I saw that and I was up to this point, I'd probably just give up on the
That's-
questions.
That's fair.
Good enough.
Luckily, you don't need that one for the general equation.
Yeah. We have one thing that with current, we can have the total voltage.
Mm-hmm.
um,
And always see what it gives the most points. Min max your points, guys. And look through all of them, do the easiest one first, and write yourself a cheat sheet. It's open book, open notes, but write down a sheet that has like this equation on it.
Do
So
you
you-
have any of your old cheat sheets to look at or no?
There's one in the Discord somewhere up in the circuits. That was my old one. You don't need to use that one. But that's where it is. But
Thank you.
yeah. Have a good one.
Oh.